Alright, so let's begin creating our game. So I just want to start by cleaning up a little bit here. And now we can start off by creating our cell. And we're going to want our cell to be exposed to the JavaScript. So let's go ahead and use WASM Bindgen to expose it. And we want it to be represented by an unsigned 8-bit integer, and then we're going to need to derive a couple of traits. So the couple of traits that we're going to want, I say couple, we're going to want many traits. We're going to want clone, copy, debug, PartialEq for equality, and EQ as well. And now we're going to create an enum called cell. And then inside of here we're going to have dead equals 0 and then alive equals 1. And so to expand on the repr U8, that's important because we want each cell to be represented as a single byte. And so the next thing we can define is our universe, which is also something that we're going to want accessible inside of the JavaScript. So we're going to say pub struct universe, and then inside of here we're going to have a width of an unsigned 32, a height which is also unsigned 32, and then we want our cells to be in the universe as well, which we will represent as a vector of cells. And so now that we have our universe defined, we can start implementing some methods on it. The first method we want to implement is accessing the cell at a given row and column into an index into the cell's vector. So we will implement some methods on our universe. And again, we want to be able to get an index into the vector. So we'll create a getIndex function. We're going to pass in self, and then we have our row and our column. And we're going to return a usize. So the logic in here is going to be pretty straightforward. We're just going to return the row times our self dot width plus the column, and we want to return it as usize. And that's all we need to do in order to get our index. And now that we have the method implemented, we can calculate the next state of a cell. So we need to get a count of how many of its neighbors are alive. And the method is going to use deltas and a modulo, which is the % sign. And we're using that to avoid special casing the edges of the universe with if statements. So we're just trying to avoid having extra if statements when we don't need to do them by using this logic. And so by applying a delta of -1, we are actually adding -1 to the height, and then we mod it. So this allows us to avoid unsigned integer underflow, meaning we went below 0, and since it's unsigned, our results would be incorrect. So let's start implementing this, and this will make a little bit more sense. So we're going to say our live neighbor count. Again, we're passing in our self, our row, and our column. And we're going to return back a U8. So we'll say let mutable count equals 0, and then for delta row in self dot height minus 1, 0 for the row, 1 for the column, and then we are going to iterate, clone, and now we're going to do the same thing for the row. So we're going to have the column, delta column in self dot width minus 1, 0, 1 dot iter dot cloned, and then if delta row is equal to 0 and delta column is also equal to 0, then continue. So now down here we can say let neighbor row is equal to the row plus delta row mod self dot height, and let neighbor call equals column plus delta call mod self dot width. And then we'll just go idx for index, self dot get index of our neighbor row, and then for our column, neighbor column. And now we can add to count self dot cells at the index as a unsigned 8. And then all we want to do when this loop is done is return our count. So all we're doing is getting the count of all the cells located, of all the neighbor cells located at that row and that column inside of our universe. And so now that we have that done, we have everything needed to compute the next generation. And we can have a straightforward implementation of the game's rules by using a match expression. And since we want JavaScript to control this portion, we are also going to place this inside a WASM Bindgen block. So let's go ahead and add it. So we have WASM Bindgen, and now we're going to impl universe again because we want this to be exposed to the JavaScript interface. And now inside of here we're going to create a function called tick, and basically a tick is a new generation. And so we're going to pass in our self, and now inside here let mute next equals self dot cells dot clone. And now we can say for row in 0 to self dot height, and for call in 0 to self dot width, we can say let idx equal self dot get index of our row and our column, and then let cell equals to self dot cells of our index, and then let live neighbors equals to self dot live neighbor count of our row and our column. And now we can start implementing in the rules. So let next cell equals match on the cell and the live neighbors. So we have rule 1, which is any live cell with fewer than 2 live neighbors dies because of underpopulation. And so we can say cell alive x if x is less than 2, then cell is dead. And now we have, we'll put another rule 2. Any live cell with 2 or 3 live neighbors lives on. And we'll just go ahead and write out the rest. Rule 3, any live cell with more than 3 live neighbors dies because of overpopulation. And then rule 4, any dead cell with exactly 3 live neighbors becomes a live cell due to reproduction. So now let's implement rule 2. So we have cell is alive 2 or cell is alive 3. Cell alive. Okay, so now we can implement rule 3. So we will have a cell alive if x greater than 3, then our cell is now dead. Excuse me. Alright, we have a little error here. What do we... oh. There we go. And now we can implement on rule 4. So our dead cell, if it has 3 neighbors, now becomes a live cell. And then otherwise, because remember, you have to handle all situations, otherwise all cells maintain themselves. Otherwise, cell remains in the same state as before. So now we can end that block, and then we can have our next iteration on the next index equals to our next cell, and we can say self.cells equals to next. So currently we don't have any way to display the game currently. So we need to implement a method that will make this easy for us to see what is going on when we execute our program. We will use empty and full squares to signify if a cell is dead or alive. So just copy and paste the symbols from the code that I provide you. So we need to use standard format, and down here we're going to implement format display for our universe, and in here we're going to have a formatting function going to refer to self, and then it's going to have a mutable formatter, which is going to return a result for us. And so in here we have for each line in the self.cells as a slice dot chunks self dot width as usize, and then for a reference to our cell and line, we're going to say let symbol equals to if cell equals to is equivalent to a dead cell. Then we want a empty, and I'm just going to copy and paste this in for myself, else, there we go, else we want that guy. So let me format this real quick to make it pretty. Alright, so let symbol equal if cell is equal to dead cell, then we want if the cell is dead, we want an empty square, else if the cell is alive, then we want a full square. That is correct. So now we want to write F and then symbol, propagate if there is an error, and now again write, but this time we just want to write out a new line character. And return OK. Alright, so it doesn't look like we have any errors, so everything seems very happy with that. So now we have a way to display out our universe. So I'm going to take a quick pause right here, that way this lecture doesn't get too terribly long, and we will pick up in the next lecture.